The physical world is beginning to execute like a cloud environment. Across engineering disciplines, manual definition is being replaced by systematic orchestration. In cloud architecture, infrastructure as code platforms like AWS CDK abstract server setups into declarative code constructs. For operational processes, tools like AutoKitteh abstract complex API interactions into resilient workflows. The next technical hurdle is applying these cloud-native principles of declarative automation to the physical construction industry. Managing complexity requires the same abstraction logic, regardless of whether the output is a web service or a skyscraper. The $15 trillion construction industry has a historical scaling problem. In the physical realm, human error multiplies directly alongside the square footage of the project. Turning a job site into a runtime environment requires treating every task as a pre-compiled instruction. Building Information Modeling, or BIM, serves as the data schema and code base for physical infrastructure. Think of AWS CDK constructs, which encapsulate configurations into reusable digital objects. BIM performs the same function, stacking mechanical and structural systems together in a unified data model. By treating buildings as pure data, civil engineers shift physical risk to the left, resolving errors in the digital domain before a single yard of earth is ever moved. A digitally compiled structure translates flat blueprints into multi-layered physics simulations. BIM analysis checks for spatial syntax errors, like an HVAC duct attempting to occupy the exact same coordinate as a load-bearing beam. The clash resolves in the math, preventing a physical collision. This digital collision detection delivers tangible results. According to Skanska, 74% of contractors report improved constructability of their final designs. This shared data model increases owner engagement. Stakeholders interrogate the structural logic and verify requirements before authorizing execution. A complete 3D model operates as a fully compiled application that has successfully resolved its physical dependencies. Executing a mathematically verified digital model yields quantifiable financial dividends. The Skanska report reveals 85% of complex projects experience a reduction in final costs, with most seeing at least a 5% drop. For power users, efficiency scales further. 10% claim over a 10% decrease in total final costs. This timeline comparison shows the impact on delivery speed. 88% of users report accelerated completion rates strictly due to digital schedule compression. Looking at the top tier of that data, nearly a quarter of users achieve over 10% schedule compression. Digital orchestration has moved from a design luxury to a rigorous financial prerequisite for surviving complex projects. In software, ambiguous logic causes a runtime error. In construction, it generates a request for information, or RFI. An RFI paralyzes project momentum. Physical work halts while architects and engineers resolve undocumented conflicts. This graph tracks how a compiled model anticipates errors. Skanska data reveals 74% of BIM users see a massive reduction in total RFI volume. Nearly half of those report an exceptional 10% or greater reduction. The economic disparity here is absolute. Resolving an architectural uncertainty digitally costs exponentially less than resolving it with idle crews standing in a physical trench. Minimizing RFIs proves that a robust digital twin successfully insulates the project from physical unpredictability. If the digital model is mathematically perfect, the physical assembly no longer has to occur entirely on site. Instead, teams compile physical modules in a controlled factory setting, shipping them only when the site is prepared for immediate installation. Skanska confirms this shift, revealing 88% of owners and contractors see reduced site labor resulting directly from increased off-site prefabrication. Exact mathematical prefabrication isolates physical risk. It shifts the dangerous, weather-dependent on-site construction to controlled, predictable factory environments. This reduction in active on-site labor correlates directly with a 37% reported drop in reportable safety incidents. Precise data saves lives. Prefabrication allows civil engineering to scale with the modular efficiency of software deployment. The codebase is perfect, and the components are prefabricated. Yet the final execution layer remains. Raw earth still needs to be moved, and foundation piles driven. The challenge lies in translating the exact digital coordinates of a BIM model into raw physical force across unpredictable terrain. This is where companies like Built Robotics provide the physical runtime for the digital plan, pivoting the industry toward autonomous heavy equipment. They achieve this using the exosystem. It is an aftermarket kit containing cameras, GPS, and inertial measurement units that retrofits existing heavy machinery. The exosystem interfaces directly with the machine's electric over hydraulic systems, taking complete physical control of the equipment without requiring a human operator in the cab. Consider the Built Robotics RPD-35 solar piling robot. It autonomously surveys locations, distributes, and drives heavy piles into the ground based strictly on algorithmic instruction. Heavy machinery no longer operates as a blunt instrument. It functions as an automated physical endpoint, executing digital telemetry pulled directly from the cloud. Zooming out, we can observe the entire life cycle of a modern engineering project, running continuously from cloud configuration to physical construction. AWS CDK provisions the cloud infrastructure, AutoKitteh manages the durable workflows, and BIM compiles the physical design. Finally, the Built Robotics exosystem executes that physical design autonomously, pulling instructions continuously from the Everest Cloud platform. Across all these disparate disciplines, the core operating principle remains identical. You orchestrate complexity through declarative data. We are watching digital abstraction and physical execution synchronize. Code and concrete are now governed by the same logic of the digital plan. Organizations leveraging this continuous automation loop are mathematically separating themselves from the competition in cost, safety, and speed. The physical world has been permanently annexed by the logic of software. The future belongs solely to those who compile reality before they build it.